Hello, I am Kumabe from the University of Tokyo. Today, I talk about our paper titled Profit Secretary for Knapsack and Matroid Intersection via Continuous Exchange Property. I will introduce today's flow. First, I introduce the Profit Secretary problem. After that, I introduce the Ixani et al.'s result for the variant of Profit Secretary problem, that is, matrix constraint version. Finally, I talk about a result that extends Ixani et al.'s result into the Knapsack and matroid intersection constraint. Let us first introduce the word of the Profit Secretary problem. Let us start by the optimal stopping, which is a model of decision making. In this problem, items arrive one by one, and we observe the value of them. For each item, once we observed, we choose it or reject it. Once we decided, we cannot change the choice. Let us see this problem by an example. The chef observes this meat with value 10 and immediately decided to reject it. Then the chef sees a cucumber with value 3 and he immediately rejects it. After that, he observes a tomato and he decided to choose it. Unfortunately, after that, he observes a very expensive durian which he wanted, but he cannot choose it because he already chose the tomato. The value of the string is a value of a chosen item that is tomato. However, we can easily see that general optimal stopping is too difficult. This example shows that. In the first example, the optimal solution is to take a treasure with value 100. If we chose an apple, the approximation ratio is very low. In the second example, the optimal solution is to take an apple. If we chose a waste, the approximation ratio is 0. However, we cannot distinguish these scenarios until we see the last argument. Therefore, in this situation, there is no algorithm with approximation guarantee. But in real situation, we can assume some property for the input. For example, we might assume that the items arrive in random order. This setting is called secretary problem. The secretary problem is investigated from all days, and there is a tight approximation algorithm. The approximation factor is 1 over E. We can consider another situation. Sometimes, although we don't know the exact value of items before observing, we might know the distribution of it. This setting is called profit inequality problem. The profit inequality problem is also investigated from all days, and there is a tight approximation algorithm. The approximation factor is 1 over 2. In this research, we investigated the profit secretary problem, that is, the intersection of those two cases. That is, we know the distribution of the value of items, and arrival order is random. Despite the security problem and profit inequality problem are investigated from ancient days, the progress of profit security problem is recent. The approximation ratio of the profit inequality setting, that is 1/2, is reached recently in the profit security problem. After that, several algorithms achieve the same ratio 1 minus 1/e, and the approximation ratio is further developed to these values. As we see, the profit security problem is the current hot topic, despite it is a combination of two classical problems. Next, we introduce Exani et al.'s framework. They extended the 1 minus 1/e approximation algorithm of profit security problem into some combinatorial setting, such as matroid constraint. The combinatorial profit security problem is a variant of a profit security problem. In the original profit security problem, the feasible domain is a singleton. In contrast, in the combinatorial profit security problem, the feasible domain is a combinatorial object, such as an independent set of a matroid. They applied the technique to many settings, such as matroid variant, bivalent matching variant, and combinatorial option variant. However, today I introduce the result only for the matroid case. Their strategy is to use a decreasing threshold to choose items. First, we consider that each item arrives at a random time in the 0-1 interval, instead of considering the random ordering. Let alpha t be some non-increasing function that determines the threshold. For current solution A and value function v, define RAV as this. In other words, it is the maximum possible future profit for the value function v. The algorithm chooses an item when the observed item is alpha t times the expectation of the decrease of RAV. Here, the decrease of RAV intuitively means the decrease of the future profit. By setting alpha appropriately, they get 1 minus 1/e approximation. Instead of the proof, we show the key lemma in their result. The key lemma is this. The left-hand side is the maximum possible future profit. The right-hand side is the sum of the decrease of the maximum future profit, where the summation is taken over element of some independent set X. Intuitively, it means that average decrease of the future profit is small when we consider to add element of an independent set X to the current solution A. Let us see the proof by example. Consider a graphic matrix and let A be an empty set. The optimal solution is like that. An independent set X we consider is like that. If we add an edge A to the current empty solution, the future profit decreases by at most the value of this red edge. Similarly, if we add this edge B, the future profit decreases by at most the value of this red edge. If we add the edge C, it decreases by at most value of this edge. Therefore, by taking summation of these inequalities, we get that the value of optimal solution is at least the sum of the decrease of the future profits. Therefore, we have the desired inequality. Now, we introduce a result for Knapsack and matroid constraint version. In this presentation, we concentrate on the knapsack variant. That is, the feasible domain is defined by the knapsack constraint. In this setting, we exactly know the weight of each item, so we know the feasible domain. But for the value, we only know its distribution until we observe it. In this research, we extend Xan et al.'s framework to treat the knapsack variant. By applying the defined technique, we obtain 0.213 approximation algorithm for this case. However, it does not beat the current best approximation algorithm, which is obtained by combining existing algorithms. However, the good point of our algorithm is rather its flexibility. Our technique can be applied to more general cases, such as Knapsack and matroid intersection case. Here, the feasible domain of Knapsack and matroid constraint is an intersection of Knapsacks and matroid constraints. And for the most value of K and L in this problem, we obtain the best approximation ratio. This is the main contribution of our result. Our algorithm is similar to the Xan et al.'s one. That is, we use a decreasing threshold and we choose an item if the observed value is at least the threshold. The main difficulty is that the same statement as a key lemma does not hold for the knapsack case. Let us see by example. Let V with a set consist of very large and expensive items and many small and cheap items. The optimal solution consists of one large item. Let X be the set of cheap items that the sum of weight is 1. We can see that if we want to add an item from X, we should remove a large item from the optimal solution, because after adding small item, there is no room for the large item. Therefore, by adding each small item, the future profit drastically decreases. Thus, we cannot have the key lemma that requires that if we add an element from its feasible solution, average decrease of the future profit is small. To overcome this issue, we introduce a fractional relaxation. The fractional knapsack problem is the problem that is obtained by the LP relaxation of the knapsack problem. For the fractional knapsack problem, we can prove that the lemma is similar to the key lemma. The different point as the integral version is that before we take a sum of decrease of the future profit, we multiply the decrease by xi, where x is the feasible fractional solution of the fractional knapsack problem. Let us see how this modification resolves the previous issue. If we integrally add an item from x to the optimal solution, we should remove a large item. But if we allow to remove items fractionally, we only have to remove a small part of the large item, rather than the whole part of the large item. Therefore, in this setting, fractional setting, the decrease of the future profit is small, in average. The exact proof is like following. We construct a continuous exchange map, that is, for each item I, it maps what part of the optimal solution is removed from it when adding an item I fractionally. We can make this map somehow like injective, and the proof is done. The key lemma is proved, but we have another problem. By directly applying extended methods framework, the algorithm may output an infeasible solution. This is because even if we can add an item fractionally, it may be impossible to add an item integrally. To resolve this issue, we divide items into two categories. First, we set a value epsilon, and an item is large if the weight is larger than epsilon, and small if the weight is at most epsilon. Let us see how this division works. First, assume all items are small. We set the RAV value by the maximum future profit, where the weight limit is lowered to 1 minus epsilon, not 1. In the fractional setting, since all items have weight at most epsilon, in this definition, we can ensure that if xi is positive, we can add I to the current solution. Moreover, the R value is not far smaller than the optimal value of the original problem. Precisely, it is 1 minus epsilon approximation of original optimal solution. Therefore, we obtain an approximation algorithm by examining it as framework, where the approximation factor is multiplied by 1 minus epsilon. In large items, the situation is rather simple. The main observation is that any feasible solution can contain at most 1 over epsilon items. This directly means that the key lemma holds for this case, without considering fractional version. To treat both situations, we extend the Exani et al. Framework to work in our situation. The precise statement lies like this. You don't need to read it, but we can apply this statement to both small only and large only case. And we obtain these approximation ratios for these cases. The final problem is to combine these algorithms. Our algorithm chooses one strategy between that only use small items or that only use large items. Note that we don't know that which strategy is better. Therefore, we choose the strategy randomly. Our algorithm chooses each strategy in the probability that is calculated from the approximation factor, like this. Then, we have this approximation ratio for single knapsack constraints by setting epsilon equal 1/2. And we can extend this result into Knapsack L-matroid constraints. In this case, an item is large if the weight is larger than epsilon for at least one knapsack constraint. And by applying a previous statement, particularly for the case L equals to 0, we set epsilon equals to 1/3 and this approximation ratio. This is proportional to 1/k. Let us summarize our result. We give a constant factor approximation algorithm for Knapsack L-matroid perfect security problem. Our algorithm is based on Exani et al.'s framework. To apply this framework, we first divide items into small items and large items, so shown by a constant epsilon. For large-only case, any feasible solution has a small cardinality, and this fact leads us to the bounded approximation ratio algorithm. For small-only case, we modify the framework to use the fractional relaxation of the knapsack problem. This modification allows us to prove the key lemma of Exani et al.'s framework, and we obtain a bounded approximation ratio algorithm. Finally, by combining these algorithms, we obtain a bound of the approximation ratio. Thank you for the listening.